Chapter 7 discusses carbohydrates and glycobiology. The overall learning goals for Chapter 7 include learning the structures and names of monosaccharides, learning the open chain and ring forms of monosaccharides, the structures and properties of disaccharides, and the biological function of polysaccharides and glycoconjugates. Carbohydrate, carbo meaning carbon, hydrate meaning water, are named this way because many have the empirical formula CnH2ON, and they are produced from carbon dioxide and water via photosynthesis in plants. They have a large range of sizes. Some are as small as glyceraldehyde with a molecular weight of 90 grams per mole, and some are as large as amylopectin with a molecular weight of over 200 million grams per mole. They fulfill a variety of functions including energy storage. They are structural components in cell walls, and they are informational molecules in cell-cell signaling, and they can be covalently linked with proteins and lipids. There are three major classes of carbohydrates: monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides, also known as simple sugars, consist of a single polyhydroxyaldehyde or ketone unit, and the most abundant monosaccharide in nature is the 6-carbon sugar D-glucose. So the word sugar is interchangeable with the word monosaccharide. Oligosaccharides consist of short chains of monosaccharide units, or residues, that are joined by characteristic linkages called glycosidic bonds. The most abundant are the disaccharides with 2 monosaccharide units. Sucrose, or cane sugar, for example, consists of the 6-carbon sugars D-glucose and D-fructose. Polysaccharides are sugar polymers containing more than 20 or so monosaccharide units. Some even have hundreds or thousands of units. Some polysaccharides, such as cellulose, are linear chains, whereas others, such as glycogen, are branched. The basic nomenclature for monosaccharides includes the number of carbon atoms in the carbohydrate plus the suffix OSE. So, for example, a 3-carbon carbohydrate would be called triose. And there are common functional groups. All carbohydrates initially, in their linear form, had a carbonyl functional group. If it was an aldehyde, we call those aldoses, and if it was a ketone, we call those ketoses. So here would be an example of an aldose, glyceraldehyde. It has an aldehyde. So an aldehyde, the functional group, you have a hydrogen attached to the carbonyl carbon. But with a ketone, you have carbons on either side of the carbonyl. So glyceraldehyde would be an example of an aldotriose. It's an aldose because it has an aldehyde, and it's a triose because it has 3 carbons. And then this would be a ketotriose, 3 carbons with a ketone functionality. So if you have a monosaccharide with 3 carbons, it's a triose. With 4, it's a tetrose. With 5, it's a pentose. And with 6, it's a hexose. So here are some examples of triose, hexose, and pentose. So notice the pentose here, there's 1, 2, 3, 4, 5 carbons. And this is an aldehyde, so it's an aldopentose. This is also an aldopentose. But notice this carbon doesn't have an OH group, so it's called 2-deoxy-D-ribose. Here we have some hexose sugars. So this would be an aldohexose because it has an aldehyde and 6 carbons, and this would be a ketohexose because it has a ketone and 6 carbons. And this is your D-glucose, this is your D-fructose. Carbohydrates are stereoisomers. Now remember, enantiomers are stereoisomers that are non-superimposable mirror images. In sugars that contain many chiral centers, only the one that is most distant from the carbonyl carbon is designated as D or L. D and L isomers of a sugar are enantiomers, which means every chiral center is reversed in its enantiomer. Most hexoses in living organisms are D-stereoisomers, although some simple sugars can occur in the L form, such as L-arabinose. So this figure just shows you how enantiomers are mirror images. When we draw monosaccharides, we can use a Fisher projection formula where we have the CH2OH at the bottom and the aldehyde at the top. And we can also draw this in a perspective formula. So with the Fisher projection formula, anything on the horizontal is interpreted to be pointing towards you, where anything on the vertical is pointed away from you. Whenever you have a compound with a chiral center, there are 2 to the n total number of stereoisomers possible for that compound, where n is the number of chiral centers. So if we look at glyceraldehyde, it just has one chiral center, the carbon shown in red, and so it would have a total of 2 stereoisomers. The other stereoisomer not shown would be its enantiomer L-glyceraldehyde. Then here, if we have 2 chiral centers, there would be a total of 4 stereoisomers, and 2 of those are shown here, both of the D isomers, which vary in the chiral configuration at that carbon. So notice that carbon, the OH, is on the right in erythros and on the left in threose. So these are diastereomers. And here's an example of sugars with 3 chiral centers. So those would have a total of 8 possible stereoisomers, and half of those would be and half would be L. So only the D half are shown here. And notice that they all have the OH group furthest from the carbonyl on the right. That's what gives them the designation of D. And then the other chiral carbons in red have different configurations. And then this would be 6 carbon stereoisomers, just the D isomers are shown, so there's double the amount shown here. But of the D isomers, notice for all of them, the OH here is on the right. That's what makes them the D isomer. And then the configurations at the other 3 chiral carbons vary amongst those stereoisomers. And here are some examples of ketoses. So dihydroxyacetone, it actually doesn't have a chiral center. However, D-erythrulose does. So it has 1 chiral center, so it has a total of 2 stereoisomers. The other one not shown would be the L stereoisomer, it's an enantiomer. Then here are some examples with these ketoses. So these have 2 chiral centers. Here the OH group furthest from the carbonyl is on the right, which designates it as D. And then the configuration of the other chiral center differs. So these compounds D-ribulose and D-xylulose are diastereomers, and then they each would have enantiomers that are not shown. That would be the L version. And then finally, here are some 6 carbon ketoses. So there's a total of 8 possible stereoisomers because there are 3 chiral carbons shown in red, but only the D isomers are shown here, so half would be D, half would be L. And they're D because all of the OH groups are on the right-hand side here, the OH on the carbon furthest from the carbonyl, and then the other carbons, the other chiral carbons, differ in their configuration. We use a special word with carbohydrates called epimers. And epimers are stereoisomers that differ at only 1 chiral center. So they are not enantiomers, they're actually a type of diastereomer. And diastereomers have different physical properties, such as melting point, boiling point, water solubility. And an example of this would be D-erythrose and D-threose. So the chiral center here, the configuration is the same, but at this carbon it's flipped. So these would be epimers. And it's also accurate to say they're diastereomers, but they're a special type of diastereomer called an epimer. So here are some more examples of epimers. So if we look at D-glucose, D-galactose is the epimer of D-glucose, where the difference is shaded in blue here. It only differs at that carbon 4. And then D-mannose is an epimer of D-glucose, and it differs at the configuration at carbon 2. But then if you look at the relationship between mannose and galactose, they differ at more than 1 carbon, so they are diastereomers but not epimers. There are common carbohydrates in biochemistry. Ribose is the standard 5-carbon sugar. glucose is the standard 6-carbon sugar. Galactose is an epimer of glucose. Mannose is an epimer of glucose. And fructose is the ketose form of glucose. You may recall from organic chemistry that aldehyde and ketone carbons are electrophilic and that they can be attacked by an alcohol. Now, when that happens, if it's an aldehyde, the alcohol, the oxygen attacks the carbonyl, and the electrons go up to the oxygen atom, which after protonation results in something called a hemiacetal. If you do that same reaction starting with a ketone, the resulting product is called a hemiketal. And these reactions form the basis of cyclization of sugars. So if we look at D-glucose here, the OH at carbon 5 will actually be the nucleophile, and it will attack the carbonyl carbon of carbon 1. And when it does that, it forms a ring. And there are two different ways in which the OH could attack, either from the top or the bottom of the carbonyl. And depending on the orientation, you'll get either beta D-glucopyranose or alpha D-glucopyranose. And all of these reactions are reversible. So the cyclization would give the ring, but then the reverse reaction would break the ring and then give the linear form back. The former carbonyl carbon becomes a new chiral center, and it's called the anomeric carbon. And the position of the hydroxyl group that's formed determines if the anomer is called alpha or beta. If the hydroxyl group is on the opposite side of the ring as the CH2OH moiety, the configuration is alpha. If it's on the same side, it's beta. 6-membered oxygen-containing rings are called pyranoses after the pyran structure, and 5-membered rings are called furanoses because they resemble a furan structure. And the anomeric carbon is usually drawn on the right side. So when glucose cyclizes, it forms glucopyranose. And here we have D for both of these because this was cyclized from the D-glucose. But the alpha, notice here, the alpha has the OH group at the anomeric carbon opposite the CH2OH group. But here, they're on the same side. They're both on the top of the pointing up in the pyranose ring. And then if we had fructose and it's cyclized, it would become fructofuranose because it forms a 5-membered ring. And you can have both the alpha and the beta forms that differ in whether the OH is up or down. So here the OH is down, which is opposite. On this opposite side is the CH2OH group, so that's called the alpha anomer, and then this would be the beta anomer. So this is the anomeric carbon. So this is the bond that was made in the hemiketal formation. So that would be the open chain form, and then this oxygen attacked that carbonyl to form the hemiketal. Pyranose rings are 6-membered rings, and they resemble cyclohexane in that they can exist in different chair conformations and sometimes even in boat conformations. And this just shows you the two possible chair forms of beta-D-glucopyranose. We can get some important hexose derivatives. So if we start with the beta-D-glucose, we can replace this OH group with an NH2 group or with an amide group to get these important derivatives. We can also add an R group. We can also get deoxy sugars where we are eliminating the CH2OH group and replacing it with something like a methyl group. And we can get further oxidized versions where the CH2OH group is oxidized to the carboxyl, or this group is oxidized to a carboxyl, or the cyclic form is further oxidized to, for example, a lactone, which is just a cyclic ester. Monosaccharides can be oxidized by relatively mild oxidizing agents such as cupric ion, Cu2+, and if something's oxidized, that means it's a good reducing agent. So as a result, glucose and other sugars that can be oxidized and therefore are capable of reducing things like cupric ion are called reducing sugars. And this behavior is the basis of a variety of tests, including Fehling's test, Tollens test, and other modern detection techniques using colorimetric and electrochemical tests. A glucose analysis can take advantage of the fact that glucose can be oxidized. It's a reducing sugar. So if you use the enzyme glucose oxidase in the presence of oxygen, you can oxidize that carbon all the way up to the carbonyl. So now it's a lactone, it's a cyclic ester. And then the hydrogen peroxide that is released will oxidize another organic molecule, such as this molecule, into a highly colored compound. And the concentrations of such compounds can be measured using colorimetry. And you can also use electrochemical detection, which is used in portable glucose sensors. Now, for glucose to be a reducing sugar, it needs to be a hemiacetal. And a hemiacetal, remember, is a carbon with an OH group and an OR group attached to it. Two sugar molecules can be joined via a glycosidic bond to form a disaccharide, and it will form between an anomeric carbon on one sugar and a hydroxyl group attached to a carbon on a second sugar. And the glycosidic bond is more stable and less reactive than the hemiacetal at the second monomer. And the second monomer with the hemiacetal is reducing, but the anomeric carbon is non-reducing. And that has to do with whether or not that carbon has a hydrogen on it. Disaccharides can be named by the organization and linkage of the two sugars or using a common name. So the disaccharide formed upon condensation of two glucose molecules via a 1-to-4 bond is described as alpha-D-glucopyranosol 1-to-form D-glucopyranose. However, the common name for this is just maltose. So let's sort through that. So we have an alpha D-glucose and a beta D-glucose coming together, and they're going to join via a glycosidic bond. Now notice the difference between alpha and beta is whether the OH group on the anomeric carbon is up or down relative to this group. So when they join together, we form this new bond here. So the oxygen on this beta D-glucose is now attached to carbon 1, and this group leaves. So this is a condensation reaction because we're losing an equivalent of water in the process. So as a result here, we now have an acetal because this carbon has two OR groups attached to it. So this would be an OR group, and this would be an OR group. So it's no longer a hemiacetal. However, the other sugar still has its hemiacetal on carbon 1. Now it's named alpha D-glucopyranosol 1-to-4 because we've bonded carbon 1 to essentially the hydroxyl group connected to carbon 4. So this is carbon 1. The anomeric carbon's carbon 1. So we connected carbon 4, the hydroxyl group on it, to carbon 1 of the alpha D-glucose. So the whole name becomes alpha D-glucopyranosol 1-to-4 because that's the linkage, D-glucopyranose. Now you can also have two sugar molecules joined via a glycosidic bond between two anomeric carbons, and as a result of this you get rid of both the hemiacetals on both sugars, so there are no reducing ends, so that would be called a non-reducing sugar. And so take a look at these molecules, these disaccharides, and see if you understand the naming convention. So with the top one here, we have beta-galactopyranose on the left, and carbon 1 is connecting to the OH group on carbon 4 of the glucopyranose. So as a result, the name becomes beta-D-galactopyranosyl 1 to 4 to show the linkage between 1 and 4, the 1 and 4 carbons, beta-D-glucopyranose. And that can also be abbreviated as this, and then the common name is lactose. And then here the common name is sucrose, but notice here we have a formation between the two anomeric carbons. So we have beta-D fructofuranosyl, alpha-D glucopyranoside, and we changed the ending to IDE because that indicates that the anomeric carbon was turned into an acetal. And so you could also abbreviate it like this, where we have the 2-beta to alpha-1, or we could reverse the order, the alpha-1 to the 2-beta, as long as it's connected with the corresponding sugar. Okay, now test your knowledge. A monosaccharide with a ketone functional group and 7 carbons is what? Which of these is true? A, can never exist in cyclic form. B, is a ketoheptose. C, is an aldoheptose. Or D, has a single chiral center. Put your answer in the chat. Question 2. Which of these is true? Cyclization of monosaccharides. A, is the result of hemiketal or hemiacetal formation. B, is irreversible. C, never happens. Or D, only occurs in hexoses. Question 3. The pair below could best be described as A, anomers, B, epimers, C, constitutional isomers, or D, enantiomers. So compare the two in each carbon in red and determine what's different. And finally, which arrow correctly identifies the atom that will become the anomeric carbon when this cyclizes? And as an extra challenge, could you draw the structure that would result from that cyclization?